Good afternoon, everybody. Welcome to our technical seminar, which is part of the 14th annual Dean Lytle Electrical and Computer Engineering Endowed Lecture Series. I'm Sriram Kannan, an associate professor here at the EC department. The Lytle Lecture Series is our department's premier annual event featuring internationally renowned researchers working in communications and signal processing. Due to the pandemic, we are holding this series online this time. We hope to return to in-person from the next time. It's my great pleasure and honor to introduce Professor Muriel Médard, who is the Cecil and Ida Green Professor at the Electrical Engineering and Computer Science Department at MIT, where she leads the Network Coding and Reliable Communications Group at the Research Lab for Electronics at MIT. She has done pioneering work at the intersection of information theory, networking, communications, and security. She has many honors. I'm just going to list a small sampling here. She's a member of the US National Academy of Engineering, a fellow of the US National Academy of Inventors, a member of the American Academy of Arts and Science. She holds all her degrees, bachelor's, master's, and PhD from MIT, and an honorary doctorate from the Technical University of Munich. She received the 2022 IEEE Koji Kobayashi Award, the IEEE Communication Society Edwin Howard Armstrong Achievement Award, the 2016 IEEE Vehicular Technology James Evans Avant-Garde Award. She's also won a variety of Best Paper Awards from the Information Theory Society, Communications Society, IEEE at large, sitcom, many places, and her research has been groundbreaking in a variety of these fields. In particular, she is widely acclaimed for her research on network coding, which she took from the very basic algebraic foundations all the way to practice and technology transfer. On a personal note, I've had the fortune of knowing Muriel for a while. She served on my PhD thesis committee when I was at Urbana-Champaign. But even before that, actually, when I was an undergrad, the reason I took up information theory was actually reading her paper on algebraic network coding. I was fortunate to meet Ralph Cotter at that time, who wrote the paper with Muriel, where they brought up this absolutely stunning idea of using algebraic geometry to solve networking problems. And that's something I would say absolutely captured my imagination to get into this field. So it's a great honor to have Muriel here to come address us on her new and exciting work on how to do universal decoding. Thanks so much, Muriel, for taking the time to be here.
Thank you so much, Sriram. What a very kind introduction, and thank you, everyone, Mariam, but the whole team for inviting me. This is really a treat. So I am going to let me stop sharing. Go to the other lecture. It's really really a pleasure to be able to delve a little bit more deeply into this topic that's so interesting to me right now, and on guessing random additive noise decoding. So again, at the risk of boring everybody, let's sort of go back to the principles of coding, what we do over and over again. So what do? We take data, say, 4 chunks of 1,000 bits each. We source code it. That's to say that we reduce the space complexity of the data. And so if our data is, denoted by, say, something like S, we can source code it by a ratio that corresponds to the entropy of S. So if I have, say, 4,000 bits, I go down to maybe 2,000 bits if my entropy is 1/2. Then I take this data, and after having done all that work to compress it, what do? I expand it again, and I expand it by a rate that corresponds to the ratio of extra expansion that I've done. So here maybe I had 2,000 bits, and I've gone to now 3,000 bits, which is a rate 2/3, okay? So 2/3 of the bits that I send correspond in effect to payload bits that I originally wanted to send. And then this X gets sent over a channel. And the reason I expanded things in the first place, it looks weird. It's like first I shrink it, then I expand it out again. Why am I shrinking things if I'm going to expand them again? Other than the fact that, of course, this is cheaper to store, and as I said, the storage complexity is what the source compression is doing. The reason I do is because some of the transmissions are going to get corrupted by noise. And we usually denote this noise through an additive effect, say flipping things from a 0 to a 1, which is like an addition in Galois field of size 2, but some effect of some sort. And the channel decoding is by hook or by crook, looking at this Y and trying to reconstruct the X. If I manage to reconstruct the X, and of course I reconstruct my payload data, and then I get back to, I can expand it and reconstruct the original source. And I could keep going like this over and over and over again with some probability of error at these different steps of sort of messing up and getting things wrong. And as long as this rate here is less than, say for a binary system, 1 minus the entropy of the noise, the Shannon entropy of the noise, then I'm okay. Okay, so let's do a little bit of counting. How many possible strings I had here? The reason I can compress from, say, 4,000 bits to 2,000 bits is that in these 4,000 bits, there was a latent space, to think sort of like a compressed sensing person. There was a latent space, which was sparse, which had only 2 to the NHS bits. So it only had 2 to the 2,000 bits, really. And that's why I can find a representation from 4,000 down into 2,000 is because underlying these 4,000 bits, there were only 2 to the 2,000 possibilities. Okay, and so that's sort of what we're using. It's that sparsity of possibilities in this, original 2 to the 4,000 space. The fact that it was really, it could be reduced with high probability to a 2 to the 2,000 space. That's what I've used here. Now, what I've used here is that I had, rather than having 2 to the 3,000 strings, I really only have originally 2 to the 2,000 strings, which is the payload. Okay, so 2 to the NR. It's not the same N here as that one, but I don't want to drag around an N and an N prime. So here N is maybe like 4,000, here N is 2,000, but we can all do that in our heads. Now, what would be the nicest noise I could ever encounter? Okay, given that I'm going to have noise, what would be the nicest noise I could ever encounter? Well, it would be a noise that sort of helpfully, unobtrusively decided to first compress itself to like the smallest representation of that noise, and then, obligingly place itself at the end of my transmission. Okay, if noise was like that, then everybody knows how to code for that. You just send your data, and then you would just leave some space blank at the end of your data transmission, or the noise would, as I said, obligingly place itself after having shrunk itself to its minimum representation. Right? That's the best thing that could ever happen, right? That we all agree that given that I need to have, say, an entropy HN of the noise, if the noise were to say, oh my gosh, I'm terribly sorry, I really didn't want to step on you, I'll just shrink myself and paste myself over here at the end, we would be done, right? So I can't do any better than that. Surely I cannot do any better than that, okay? And basically that's what, however, is what we're saying we can do. And let me explain why. So we have this Y, which is X plus N. Okay, how many channel outputs do I have? Here I have channel is 3,000 bits, okay, of output. So that means that I have 2 to the 3,000 possibilities max for my channel output. My channel inputs here are 2 to the 2,000 max, okay? If I tell you that I'm able from Y to recover X, because I have addition here, but think of addition as being any sort of invertible transformation, it means that from y, I can also recover n, right? Because if you give me y, I see y. If I can recover x, it also means that I can recover n, which means that there has to be enough information there to recover n. Now you're going to say, Muriel, I didn't want to recover n, right? I don't want to send the noise. The noise is bothersome. Yes, but if I can recover y, it must be that I'm able to recover n, right? How many possibilities are there for x? 2 to the nr. How many possibilities are there for n? Well, by the same token as why we can do compression, there's 2 to the nhn with high likelihood. So if I'm able to, if for every y, of which there are 2 to the n maximum, I can recover for every code word, I can recover with high likelihood the noise. It must mean that this product has to be less or equal to 2 to the n, right? It's just a pigeonhole principle. All right. So then what does that mean? It means that n, which is here on the left-hand side in the exponent for the number of possibilities for y, has to be greater than or equal, because that's the maximum total number of possibilities for y, greater than this product, because for every x, I need to be able to recover with high likelihood all the n's, and with high likelihood, this is how many n's there are. So 1 is, and this is where I'm going to use my annotation. Yes, thank you for making that possible. So what I have is 2 to the n is greater than or equal to 2 to the nh. I'm not going to put the n, just going to call it h plus r, which means that 1 is greater than or equal to h plus r, which means that r is less than 1 minus h. Okay. So that's basically what we have. That's basically what we have. And that's where capacity comes from, right? The best thing that I could do is to have, you know, the converse, in effect, is to have the noise all go at the end. Okay. Now, Shannon's idea for channel coding was pick a code book randomly, the way I described in the first talk today. Take these 2 to the n possibilities, pick a code book randomly, and just pick 2 to the nr out of all the possible 2 to the n strings uniformly at random with replacement, as insane as it sounds. Why with replacement? Just because it's easier to analyze. I'm going to pick some subset. Now, again, remember that basically if n is large, what do I have is that if n is large, what I have is that 2 to the nr over 2 to the n. So the ratio of possible code words messages over this, the number of the code words that I could be picked to, this is going to 0 as n goes to infinity. Okay, so my sparsity is becoming infinite. I'm basically getting an infinitely sparse set of code words among my possible code in my code book. Okay. So this 2 to the nr, which is a vanishing proportion, even though my r, which is the ratio, so say 2/3 in the example that I gave you, is fixed, that proportion is going to 0 as my n, my length increases. So I pick at random these code words. Okay. And then when something is received, I compare, so say that I send this one, but something was received which does not correspond to a code word. Okay, so this is what was sent over here. This is what was received over here. Then what's going to happen is I'm going to look over all the possible code words, and I'm going to see the one that maximizes this probability a posteriori. Now, why can I look at the maximum likelihood rather than look at the maximum a posteriori? Because recall that we had done, to start out with, that we had done compression, right? So this compression here had made all of these possible transmissions in effect equally likely. So I can't do anything clever around trying to figure out which message was most likely to be transmitted. I've already subtracted that information out in order to have the most economical representation. Okay, so I do this. I choose the code words, then I set a code word, then I look at the received code word, and I try to decode. Now, our new algorithm, which is guessing random additive noise decoding, is an ML decoding for channels with additive or invertible noise and arbitrary code books. The decoding is determined by the complexity of the noise guessing. And unlike Shannon's ML decoding scheme, it requires less computation at higher codebook rates. So again, let's look at this coding scheme. In this coding scheme, the size of the codebook is growing exponentially with n. Therefore, the complexity of looking at this maximum is growing exponentially with n. For us is actually going to be it's going to exponentially with r, okay? So as r gets higher, this is growing exponentially with n and r. For us, as r gets higher, actually our complexity is going to go down because we're basically looking at the door. And you can also, it shows out actually, and I mentioned that a little bit in the Q&A in the last lecture, you can also do abandonment, which is also approximate maximum likelihood, but is also capacity achieving, where you basically guess, and if after a little while you haven't guessed, you go, you know what, forget about it. And it turns out to be extremely effective with even fairly low abandonment. So it's practical for high rates. Small, we'll see small is not really small, it's thousands, and you'll get low complexity. So what happens with GRANT? So it's based around guesswork, guessing the effect of the noise. Now, if I only had one code word to send and I sent it, and I kept guessing the effect of the noise, eventually I would identify the true noise, right? I mean, eventually I would go, okay, oh, I hit the one code word, right? But of course, I don't want to send one code word that's like a rate of 0, okay? I want to send a lot of code words. So the difference between the transmitted code word and other code words is what a code word difference noise that I don't want to hit. So I'm going to make an error if I guess the noise effect, which corresponds to the difference between what was transmitted and a different code word. We're going to call that the code word difference noise. I should, shout out to Andrea Goldsmith. When Ken and I, we were presenting this to her, she suggested, she loved the idea, and she suggested this, this terminology for code word difference noise, which I like, okay? So for me to get an error, it has to be that, when I receive this, when I guessed maybe to over here rather than to over there, because I guessed a code word difference noise before the true noise. Okay, so what do I have? I have a race between guessing the true noise, which will get me to the right code word, and guessing one of the code word difference noises. Okay, that's when I'm going to make an error. There's only one true noise. How many code word difference noises are there? Well, as many as there are code words in the code book. Okay. So I have this race between true noise, correct output, code word difference noise, incorrect output. If I have a random uniform code book a la Shannon, the location of these code word difference noises is uniform. right? Because I chose these code words at random. So for every bit in a code word, there's a chance 1/2 that that bit is the same as another code word in the same code book. Does that make sense? Right? Like for every bit in a code word, there's a probably 1/2 that it's the same bit as any other bit in any other code word in the code book, because they were chosen all at random, right? So the code word difference noises are basically 0, 1 with probably 1/2. Okay, that's really sort of the insight. Okay, so I have 2 to the NR, well, really, 2 to the NR minus 1 code word difference noises. Okay, because everybody but the correct code word. But forget about the -1. Let's look at 2 to the NR, which should be sufficiently bigger than 1. I can ignore that. And now I'm guessing over a uniform distribution over 2 to the n possibilities. How long until I guess one of them? Okay, so guessing any one of them on average, okay, would take me, sort of half the time to guessing the whole length of the system. Okay, so basically what's happening is, think of it basically at every guess that I make of a and by the way, obviously these code word difference noises have nothing to do with the true noise, right? Because they were chosen independently. The noise had nothing to do, is perfectly independent of the code word difference noises. So what do I have? At any one guess, I have a probability of 1, okay, to the n of guessing one particular code word noise of one code word. How many such code words do I have? I have 2 to the NR. So, and they're all independent. So just simple bound. I basically at any one guess, I have a probability 2 to the n 1 minus r of guessing. So if I have a probability 2 to the n 1 minus r, and I think of Bernoulli guesses, then the time until I guess is going to be the inverse of that. Sorry, r minus 1. Yeah. So the time until I guess, because I have this Bernoulli process, which has a probably 2 to the n r minus 1 at any time of coming out heads, coming out correct, the time is going to be the inverse of that, which is 2 to the n 1 minus r. So that is the number of expectations until I hit an error. Okay, so that's the number of expectations of times until I hit an error. So the average guesses until an error are 2 to the n 1 minus r, and error is one of the code word difference noises. The average guess to the actual noise, actually, if I want to hit the actual noise, is not quite the Shannon entropy, as it turns out. It's actually a slightly different, quantity, which is the Renyi entropy of order 1/2. This was something that had been found by Massey in the 70s, Jim Massey in the 70s. So think of the Shannon entropy as being a limiting Renyi entropy of a different order. This is a Renyi entropy of order 1/2, where h of 1/2 is greater than h of 1. So you would think, okay, I have to guess the correct noise before I guess one of the code word difference noises, which would mean that r is less than 1 minus h 1/2. This, incidentally, does anybody know what this is? I'll take I'll take it on the line or in the chat. Any guesses what this quantity on the right is? This is the cutoff rate. This is the cutoff rate, guys. And the cutoff rate was for a long time sort of the folk theorem of the best rate that you could get, which is the best rate that you could get really with algebraic codes of the, block or convolutional type. The cutoff rate is less than capacity because this is less than 1 minus h. Okay. Now, if you read Erdal-Arikan's beautiful paper as to how he came about with polar codes, he had shown in the 90s, and with basically nobody caring at that point anymore because turbo codes are around and cutoff rates were considered to be a superstition of the past. He had shown that codes, tree codes such as convolutional codes could not have a rate higher than cutoff. He had shown it. It had been sort of a folk theorem up to that. He had shown it, but at that point, people are like, well, we don't care about those. We now have our capacity achieving codes. And then the way he came about thinking of polar codes is he was looking for codes that would have a higher cutoff rate. So he kept improving the cutoff rate until he got the cutoff rate to be H. But this is the cutoff rate of tree codes. Okay. Now what happens is this at this point looks like, wait a minute, if you're guessing the noise until I guess the right noise, you're not going to get to capacity. You're just going to get to the cutoff rate. What gives, Muriel? Well, what it gives is the following. We don't actually going to guess the true noise. The reason guessing the true noise sometimes takes a long time, and this is connected to a question that I think I got during I think Matt asked a question there about, the sort of the tail, right? The reason it takes a long time to guess the true noise always, if you always want to guess the true noise, it may take a long time because of the tail. It actually, our analysis originally came from guessing passwords. The reason it's hard to guess a password is either you guess it pretty quickly or it's going to take a long time. Okay. But by the time you've gone past a certain amount, you're actually going to hit another code word. Never mind guessing the true noise. Remember, we're not actually interested in guessing the true noise. We're actually interested in X. We're only guessing N because, there's a lot of possibilities for X and with high probability, there's fewer possibilities for N. So we're going to guess with high probability the noise after what we call the typical set of 2 to the NH noises. And, the few times when we don't get to guess the true noise, who gives a darn? We just made an error anyway, right? We weren't interested in the noise anyway. So that's why we get to capacity. Okay, so with high likelihood, we're going to guess the noise in 2 to the NH noises, not the average time until to guess the true noise, but the average time until we guess the true noise with high probability, not absolutely guessing true noise, but with high probability. That's going to be after making 2 to the NH guesses, and as long as 3 NH is less than 2 to the N 1 minus R, which means that R is less than 1 minus H, we're done. Okay, so we started out by saying, there's no way that I could do better than just having the noise sort of compress itself and stick itself at the end to get out of the way. And now I'm telling you, if I use a random code book, I can get there. Guys, this is the easiest proof of the coding theorem you will ever see. Okay. If you find an easier one, tell me. So, with that in mind, just to give you an example here, if I have a length 200 and I have, very high bit probability here, probably 10%, but just to give you an idea, the average code guesswork. So this is a heat map. It goes from, it's a CDF, sorry, it's not a CDF. There's a number of guesses per bit in each layer. This is the Shannon typical set. This is probably 99%. And this is the average guesswork. Okay, the Shannon typical set happens way before we hit the average guesswork for the noise. So if I look at the number of guesses until the random length and noise is identified, it turns out for a broad class of noises with memory, including with memory, and I'll show you that in a little bit, this quantity, which is 1 over n log of the number of guesses, actually satisfies a large deviation property principle. And the rate function is actually related to the Renyi entropy rates, you know, this 1/2. So this 1/2 comes in the probability of error. So you have these uniforms, which are these noise codeword difference noises. There's to the NR minus 1, okay? Uniforms, which also satisfy an LDP. And the coding theorem is actually the probability that you guess one of the uniform codeword difference noises, of which there are 2 to the NR minus 1. Before you guess the actual noise is this probability you can deduce from the LDPs, and you get error exponents, okay? So basically the complexity is the number of guesses to decoding, and you can get the LDPs to show you that complexity for these error exponents. Okay, and the complexity is very low. Interestingly, you know, the math that we did for this was originally for multi-user guesswork. Excuse me, was for guessing passwords, was out of security. So we were actually looking at security issues with password cracking, okay, for things like botnets. And then we took this to, to communications. Okay, just to give you an idea, if I use sort of that Shannon inspired, you know, guessing from the message, which by the way is the way the proof of the cutoff rate for tree codes went about, which was, you know, guessing from, you know, tree codes are a way of building codes that where you make guesses as you go along, okay, in the decoding. But from the message, you know, you can see as the complexity of decoding goes up very, very quickly. For grand, the complexity of the decoding doesn't change. It only depends on the noise. At some point, actually, it dips down. At the point where your codebook rate is high enough, it dips down because you're actually more likely to make an error, right? You're going to hit a different code word before you hit the noise. But because it basically doesn't change with the rate. And when it does, it's just to go down when the rate is high enough. If I have a Markov process, by the way, if I have a Markov process, it turns out you can guess faster. Why? Because any sort of structure, correlation, you know, that I have in my Markov process is enough to make my guessing easier. You know, in the same way that in passwords, you try to, you know, make things as independent as possible so the password is the most difficult to guess. An ID noise is actually the worst thing to guess, right? Because there's no structure. Any correlation is going to give me some benefit. Okay, how well do I do with this, particularly with the kinds of short codes that we mentioned in the first talk we really are interested in getting? Here we go. Here are some curves that actually come out of a repository that's maintained by one of my colleagues at MIT, Yuri Polyansky, which is called Spectrum. And it's just a nice repository of, it's like a little collection of curated bounds and approximations. Okay, I'm actually not showing his approximations. There's that unfortunately in these areas where we're really thinking about 10 to the minus 2, 10 to the minus 3 and below. His approximations are very poor. They're actually often above capacity. So I'm only showing the bounds. In case you are familiar with spectrum, you go, Muriel, where's the approximation? The approximation is not useful here. It's above the converse, okay? So here's a converse. So here's the code length on the abscissa. Here's the rate on the ordinate. So here's the converse. It means I can, at this length, I can never get above it. Here's capacity, but because I have a finite length, I don't have infinite n, I can't get above it. Here are two bounds. Who cares what they are? The point is that these are theoretical bounds, right? People don't say, oh, here's my RCU decoder. No, it's an achievability bound. It's a wishful thinking bound. Okay, there should be a way of getting this, but good luck finding. All right. Remember, these are the kinds of codes you can get. Now you're going to say, Muriel, I can make holes, I can puncture. Of course you can make holes, you can puncture. It's messy, it's unsafe. It's like running with scissors. You can make holes, but you might also end up making a hole in yourself. You should not run with scissors. You should not puncture codes. Okay. And so let's compare. See here, I have the quotable code length. This, so basically these bounds, it's like, these bounds don't look anything like the codes we make. Like you say, oh, what if I want 85? Well, good luck getting 85. There's nothing at 85 unless I make holes, which might actually break my entire code unless I'm really careful. Okay, this is what I get with random linear codes. Above the best known bounds, within, spitting distance of the converse. So these are RLCs. These are random linear codes. And remember, random linear codes exist at every rate, at every length, okay? So if I have hard decision, that's to say, my receiver decides a priori 0, 1, and then a posteriori fixes the mistakes in 0, 1, this is a hard detection capacity for so for 10 to the minus 3 probability. A bit flip, basically this is what Grant can do, okay? So again, it seems counterintuitive for us. If you want low rates, you should go to shortcuts. And if you want high rates, you can do short or long. It's up to you, no problem, right? You just don't want long codes that are low rate, which is of course what people are using now, but people are using them now not because they want to, but because they're stuck with existing codes like LVPCs. Everybody wants short and everybody wants high rate, okay? We've been doing middling rate and long because we've been thinking code-centric decoding rather than noise-centric decoding. Okay, so how does this translate into an architecture? I'm going to show you a little bit more of the architecture of the chip that I spoke about before. Basically, what you do is we're using the code just to do a checking of whether something is a valid code word or not. And we do that by doing something very standard, which is called computing the syndrome. The syndrome is the hash, the check, okay, of the code. If it's 0, you got something in the code book. If it's not 0, don't, try again. And what happens, and one of the reasons we have such good possibilities in terms of energy, in the end, the funny thing is, if we were to redo the chip now, and of course we're working on the next chip, we will do much better, because in the end, we were afraid that the guessing would take a lot of energy, that we'd have a lot of guesses, which is sort of a natural fear with a new algorithm. It turns out it's the stupid syndrome computation that was taking the most energy. So we didn't optimize the syndrome computation, which is like I said, it's stupid because it's like everybody does a syndrome computation, right? It's like, it's like the tying your shoelaces of coding, like really your syndrome computation, that was the dominant effect in the end. But what we're able to do is, if you don't have many errors, which happens with the vast majority of the time, we can sort of run at a low frequency. And if it looks like we have more errors, only then do we sort of kick in a secondary circuit that guesses more errors. Going back to Sriram's question in the first talk, what we did is we parallelized the heck out of this. Okay, and then, and this goes back to the question I think Matt had in the first talk, then if we end up with something that had more errors, of course, we just sort of have to do a reordering. And it turns out we have a tag-based reordering, which is very, very easy and very, very fast in case of out of order systems. Okay. And somebody had asked about, again, I think it was Matt, about out of order latency. It turns out, again, our out of order latency overall is very low. Oops. Okay. One of the things that's really interesting is because we have a universal decoder, we are able to upload, sorry, there's animals outside making noise in case I don't know what they're up to, but we can on the fly change the code. And just so to bear this in mind, it means that right now, when we change a code word, maybe because the channel conditions have changed, the sender and the receiver, never mind that they only have a few choices, remember, because we only have because now we need to have a different chip for every code word, for every code book, including sometimes different rates of the same type of code, you get a different chip, right? That pile of chips I showed you before. There needs to be this coordinated dance where I say, okay, I'm going to change, I'm the sender, I'm going to change the code word. And you go, okay, Muriel, I got it. You're going to change the code word. Ready? Ready? Go. Okay. And there's like that whole wasted time where we're like, trying to figure out, are you going to catch my changing code word? Here I go. Hey, I'm going to be changing the code word to this. And then you just get the new code word and you just upload it and you start decoding both of them together. The one that's decoding correctly is the right code book. And then when I change it, and you just notice on the fly, you're like, oh, that's not working with the first code word. Muriel must have changed her second code book. Okay. No coordination. Okay. If you're in comms and you know the pain, the suffering of that, change of code books, this is a breeze, right? There's no dead zones. Okay, and you can show how we can load the matrix. These are the measured latencies. Again, going back, I had promised Matt I would show you the different latencies. So you see the vast majority of the time you have very small latency in cycles, basically nothing. And you can see the latencies for different bit error rates. Okay, and you can see how much is just the IO latency versus the out of order latency. Okay, I've shown you this table before in the main talk. I just wanted to point out a couple of things. So, we publish grant, and there are groups out there that have been doing synthesized designs. There's a group in McGill with Warren Gross, is the department chair there. They've been doing synthesized designs and seeing synthesized designs for grant coming out of Huawei recently. Okay, so there are other groups doing synthesized designs. We're the only one to have actually made a chip. Okay, again, for all of those of you who know the subtle joy and not so subtle tortures of making a chip and having to get everything to work, you know the difference. But there are other designs out there. So there are different ways of doing things than what I just showed you, but again, this was our first chip, our first try. Okay, how about channel burstiness? I showed you a little bit this in the first talk I gave. Here's an example of a Burley-Kent massive decoder for Bose-Chaudhuri-Hockenheim code. And what happens is if you interleave, you get this curve here, which is a turquoise curve. And you can see that the Burley-Kent massive decoder for binary symmetric channel, which is a great decoder, does about the same as the grand decoder, okay, which is also in dashed lines in blue, okay, because of course grand is maximum likelihood. Now, what we're doing here is we're looking at different order Markov channels, okay, and basically what's happening is this G here in the Markov is indicating how much memory there is. Okay, so the maximum memory is here for this G.025. Okay, and if you use a Berlekamp master decoder and the channel's more bursty, then your performance is getting worse and worse. But this is EB over N0 is the energy per bit over the spectral density of the noise. Okay, this is a common measure of cost, if you will. So EB over N0 is energy that I need to spend per bit transmitted, normalized by how much noise power there is in the system. Okay, blur is the block error rate. Okay, which is the probability of getting a wrong decoding. Here's the BCH 127 length. So if I use a conventional decoder, it may be okay when when everything's ID, but as the channel gets more bursty, it's going to get worse. You need more energy. For us, it gets better unless the memory is so large that it's basically the memory, the mixing time is above the length of the code by quite a bit. Okay, in which case you get this line over here. So we get a power factor of over 2, we get over 3 dB, but the interleaver that gives me that, that curve here, which is that turquoise curve in the first place, that interleaver, if you look at the standard IEEE interleaver, is over more than 100 bits. So you're paying a delay of over 100 from the interleaving, right? We always think of, codes and then the channel's interleaved. The channel's not interleaved. Your code is interleaved, okay? The interleaver delay hits you. It's not like you just get to, it's not, I know we think of interleaved channels, but they're not, right? The interleaver is costing you. So we actually presented this Ken presented this with our student Wei An, and the title of our talk at the end of last year at GlobeCom was "Ditch the Interleavers." So that's a sort of subtle messages we go for. Okay, how about using soft information? The tip that we did had hard detection, just because you need to start somewhere. But soft information obviously is extremely useful, where you have in effect a continuous representation of the output from which you can tell, well, I know that I called this 0, 1, but actually it was very close to a 0, it's just a little bit closer to a 1 or vice versa. Okay, so then the binary phase shift keying, which is you're setting +1 or -1, here's a representation again with heat maps of the soft information. So we can do soft grant, which uses soft information to produce truly soft maximum likelihood decoding, which up until now is not doable. We can use a soft reliability grant, which targets guessing by just looking at the bits that are safe and the bits that are not safe, and just looking at the bits that you're not sure about, and sort of keep leaving the bits that you're sure about alone. You can also use ORB grant, or ORB stands for Order Reliability Bit Grant, which uses codeword independent quantified soft detection for approximate ML. Okay. How do people use soft information now? In more ways than we can shake a stick at, but let's look at sort of the state of the art, which is for CRC-aided polar codes. This is the Talan-Vardy scheme, which was licensed by Samsung from UCSD a few years ago. The way you do it is you have this signal, you demodulate it from whatever electromagnetic signal was into, the binary bits. You do list decoding with successive cancellation. Use the polar code to come up with a list of possible decoded words. And then you apply a CRC, cyclic redundancy check, which is just a verification hash, to pick from that list which one is the actual code word. Okay. And this is the state of the art right now. Usually in chips, the list is about a size of 8. Note that the list size has a, the complexity of the decoding grows exponentially with the list size. Okay. So we can either do grand, which is hard detection. We can do full soft grand. We can do orb grand, which is an approximation to S grand. Let me just give you a couple of little nuggets. Here is with a 5G compatible CRC aided polar code. So in 5G, you can either have 11 or 24 bits of CRC. Here is with a list size of 16. Okay. We get, instead, we get over here. Okay, so we are, in terms of, again, energy, we are, whatever, 2 dB better. Okay, if you wanted to look at it vertically, we're whatever, yeah, 100, 1,000 times better. I mean, we're ridiculously better. Polar codes, by the way, which are capacity achieving, are not that fantastic in practical lengths. Okay, this is not something we noticed. This is something here, Henry Pfister and other people had pointed out before. But this is confirming it, if you will. But you can see that grand does as well as successive cancellation, right? I mean, we do as well as, because again, grand doesn't give a hoot. By the way, we're not using that 2-step decoding from this, first drawing a list and then doing CRC. Polar codes are linear, CRCs are linear, the combination of the two is linear. So we're still just checking one syndrome for the whole thing. Okay, we're not doing 2-step. We're just, never mind that it's a sophisticated code. Okay, we have an optimal dumb approach. So we take a sophisticated code and we use it like it was just a hash. Okay, you give me this beautiful Ming vase and I'm using it as a bucket. Okay, that's basically it. But now look at what happens with, a CRC 24. It does better. Okay, sorry, a CRC 11. It does better, but we do as well. As a matter of fact, other than the polar codes, which don't do well, we can even just do only CRC. All of our redundancy bits are a CRC, which, by the way, if you're encoding, CRC is like, is a risible code. It's just an easy to compute hash. That's its only purpose. It's embarrassing. People don't, very few people construct CRCs, and it's because they have a very strong sense of self and they don't mind everybody else poking fun at them. Okay, we should stop poking fun at them. They're actually constructing codes which are as good as the state of the art. So all codes are good, going back to what I mentioned in the talk before. And, by the way, again, here, I'm just using the interleaver, the polar code, the CRC. For me, it's just one matrix multiply, another matrix multiply, another matrix. I don't care. It's just one check. Okay. And so we can keep doing that. And by the way, random linear codes, how do they do? They do as well as polar codes. CRCs do as well, CRC-aided polar codes. Random linear codes do as well. Random linear codes, which everything does well. Okay, I'm not going to bore you. Interleaving, I already told you about it. Okay, so this is on new vision. Concentrate on the noise. Low latency, do not rely on interleaving. Ignore capacity, just try for the highest rates available at short block lengths. Anyway, it's not like we were getting close to capacity right now. We're using capacity achieving codes, at a very large distance from capacity. We have flexibility. We have an efficient, accurate decoder for all short codes, and we have robustness. We're not going to find the noise correlation. If there's a noise correlation, we'll use it. And with that, I have 2 minutes to go and I will stop.
Thanks so much, Professor Médard, for the great talk.
Thank you. I think I should try to go someplace where I have light. I want to show you my beautiful sunset here. But there's no light. So.
As Professor Médard gets set up, are there any questions? If you have questions, please either raise your hand or post them on the chat. Oh, Luis, please go ahead. You're muted.
Louis, you're muted. Okay.
3-round won't. Okay.
Great.
So what kind of channels would break grand?
That's a very good question. Because in a way, what interleavers have been doing is create the worst possible channels for grand, right? So we already sort of have been dealing with these BSCs. I think the worst channels for grand, right, would be channels where I don't know, because if you have no idea what's going on, you would interleave, right, which is what we do now. And then you would get to the worst case, which is IID, which we can deal with. That's what we designed for originally.
Not only IID, but uneven marginal distributions for the noise, right? And the two ways to get low entropy. One is memory, and the other one is have unequal probabilities, say.
Yeah. What happens is, if you really don't know what's going on, so anything, if you have unequal probabilities, yes, again, that makes our guessing easier. I mean, that's basically what people do with passwords. Again, if you really didn't know what's going on with the noise, your channel, you would probably have interleaving over, and then we're back to ID, which is, back to where we are now. So again, because it's maximum likelihood, it would break when, after current systems break, right? I think that basically what would happen is the following. If you had really, really bad noise and you had to work with very high levels of redundancy, then the complexity would be bad. Okay. The thing is, most systems, sure, yes, that's fine. Sharon just says it's okay to go a few minutes over. Yeah, no problem. I'm waiting for a horde of hungry teenagers to come in through the door, at which point, I will just open, I'll just open the fridge and step back. Yeah. So
well, this
I
is
think
this
yes.
is for me, Muriel. You can go on to someone else's question, but I get your answer.
Yeah. So I think that basically, if you end up with a channel where you're going to have to put in a lot of redundancy, it's not so much about the rate or the length, but you're going to have to put in a lot of redundancy, then, the complexity will go up. The complexity is going with the redundancy in effect.
Thank you.
Any other questions? I have a quick one before. Oh yeah, go on.
Oh, this is Kalev here. I was gonna ask you about the equalization. Do you see grand working better with equalization? You mentioned that in the first talk. Can you comment on that?
So we actually have some other ongoing work, which I didn't talk about, where we do something called noise recycling. And in noise recycling, rather than doing equalization like you would with, say, a zero forcing filter, okay, we actually use the realization and remove the realization, and we get almost the entire benefit but without having to do joint decoding. So, and of course, GRAND works particularly well for that.
Okay.
So it's actually allowing us to get equalization style results without doing the equalization.
Okay, thank you.
Um,
I ran across your, I'm working in high-speed data center networking standards, electrical measurements, actually, not so much in coding. And by the way, I was a TA for Dr. Lytle, so I appreciate this series here.
okay, fantastic.
And I may even have some textbooks that he was sharing when he retired and cleaned up his office in the old EE building that I'm not sure how many people here would ever remember, but I was a grad student at the time.
Oh, that's fantastic. That's fantastic. Yes, I mean, data centers, I think you asked a question about data centers. So again, I haven't worked in data center in a few years, and I know it's always very risky to sort of extrapolate, you know, in engineering things change. But I mean, certainly, you know, the bit error rates are not huge, right? I mean, you know, these are nice channels.
Well, with PAM4 and 1.6 terabit per second, obviously we can't have any more of these 10 to the minus 12 BR rates. So
yeah,
it's getting worse there as well.
It's getting worse, but it's still pretty low, right? So I mean, the thing is, you know, again, going back to that 2D and H. So, you know, even if you're working, I don't know, at like, you know, 10 to the minus 6, which would be super high, right? Bit error rate. I mean, you're usually working below, and you're working with codes. I mean, you know, long codes are around 10,000, right? So your codes there are still, you know, the code lengths there are still such that the, you know, n times h is small. Let's put it that way, right? And remember, it's the amount of redundancy that matters, not the, you know, not the actual length. It's not the n, it's not the h, it's the nh, right? So, you know, given that your bit error rates, yes, I realize that you may have gone from 10 to the minus 12 to 10 to the minus 9, but, you know, your codes are still not a gigabyte long, right? So you should be okay. You should be okay. You should be able to use this.
Thank you.
By the way, I forgot to mention, there is a GRAND Decoder website. So everybody, if you're interested, go check it out. It's called granddecoder.mit.edu. And so there's a website, we have papers, we have a little video, we have some explanation. And very soon, we're actually going to release the C code for you know, for GRAND and different variants of it. GRAND, ORB GRAND, and so on, we'll put it there. So it's easier to do research. We do everything in C. It's either MATLAB or C.
May I also ask a very quick question?
Yeah, Armin, go ahead.
Hi, first of all, great talk. Thank you, Muriel.
Thank you.
I was wondering how much of this also extends to multi-user communication.
Yeah.
Sorry.
Yeah.
So sometimes we have like this interference where we treat it as Gaussian noise. Do you think we can just guess them?
That's a good question. So we actually have done some work on the Mac with GRAND, and we don't treat the interference as noise. You know, I think that treating the interference as noise is, again, one of those accidents from how we first looked at the problem, right? And we sort of got caught up with that. Interference and noise are different things. Okay, interference that, you know, you're never going to decode because you don't know the code word. Okay, that's noise, right? But in the Mac, that's not the case. Interference is the other user. And this is a maximum likelihood decoder. Okay, so in order to be able to resolve a Mac, you need to know the offsets, you know, in time of the two users, right? So here's user 1, here's user 2, right? and they're going to be offset, and maybe one has higher amplitude, lower fading than the other. Maybe they're off in the phase. Okay, and everybody bear with my puppet engineering here, right? Finger puppet engineering. Now, the first thing I'm going to guess the noise effect. And now I'm going to look at this funky combination and see if, let me do this, give me a second. So there's two parts. If I only had interference and I didn't have noise, and I look at the rate of the two users, R1 and R2, basically what I have is two users. I have Y is equal to X1 plus X2 plus noise, right? If there was no noise, the best thing that I could do would be timeshare. I would just have like this 45-degree angle line between R1 and R2. Okay, because there's noise, I don't get that, I get something which is what we call, the Codeword region, which is below it. Okay. Okay, this is at 45 degrees also. It's parallel. So this is what we're going to do. We're first going to guess the noise effect. Now I'm back to having just a sum of two of them. If I do two transmissions, as long as there's a little bit of a shift, even by just one bit or, between the two of them, I just have two linear combinations. And this is actually then looking like a network coding problem. I have two linear combinations. I can undo and check, because I sent X1 and X2 twice, because the best thing that I can do is timeshare, right? Which is X1, you send, X2, you send, right? I don't need to coordinate X1 and X2. They just send whenever they want. Okay. You just say, okay, I got a linear combination here. I got a slightly different linear combination here. Between the two of them, I'm able to recover the two X1 and X2. If that works out, done. If it doesn't work out, guess the next noise effect. Check whether that gives you a linear combination of X1 and X2 that works out. So you completely separate the noise from the interference. The interference you check basically using zigzag decoding, like the stuff that Cathy Dinekatabi and her group did. Okay, and the noise you get rid of through Grand, but you completely separate the noise from the interference and not the same effect, right? Moreover, when you're looking at, the AWGN and you say, well, the other user's is like noise to me, he's not Gaussian, right? I mean, we model him as Gaussian. Nobody sends a Gaussian signal. You cannot send Gaussian signals. Okay, that's not what happens. It's an approximation. Here, you're actually making use of the fact that what you're sending is now Gaussian. Moreover, you don't have to coordinate the code words, right? User 1 can be using one code book. User 2 can be using whatever the heck other code book they darn well please, and it all works out. Does that make sense?
Yeah, totally. Is it correct to say that the syndrome computation will be significantly larger?
No. So that's a good question. I haven't looked into the complexity of syndrome computation, but I don't think so, because basically what you're doing is you're doing zigzag decoding, and post zigzag decoding, you're doing the syndrome computation. But you've already taken out the noise, right? So I don't see why.
That makes sense. Thank you.
Yeah. But zigzag decoding only works at high SNRs, right? Here you can be at lower SNR because you've taken out the effect of the noise first. So you first guess the effect of the noise and then, yeah. So I don't see why I would be, but I could have missed something. Welcome.
Thank you.
Any other questions? Okay,
If not, let's thank our
Thank
speaker
you.
for graciously giving this talk and taking the time to answer all the questions.
Thanks a lot, guys. Thank you very much. Oh, there's something in the chat I didn't notice. Oh, it was you. Sorry. Ask me if we could go over 5 minutes. All right. Hey, thanks a lot, guys. Thank you for the invitation. Take care. Bye-bye.
Thanks so much, Muriel.